Hi, everyone. We're going to get into the last section of Chapter 9, Section 9-7, which deals with inverse trigonometric functions. So we're going to take a look at the inverse sine function, the inverse cosine function, the inverse tangent function, and how they differ from sine, cosine, and tangent, respectively. We'll take a look at how we evaluate inverse functions. We'll take a look at how we take the composition of a function and its inverse, and vice versa. So first thing we want to do is we want to take a look at the sine, cosine, and tangent functions that we looked at in the previous two lessons. So when you look down below, we have the graph of y is equal to the sine of x, graphed in black. We have two periods of that function. And if we want to find the inverse of that trig function, we have a problem because we said way back earlier in the school year when we looked at inverse functions, uh, in order for the inverse of a function to be a function, we said that the original function needed to be 1 to 1. And to be 1 to 1, that function has to pass the horizontal line test. Well, when we look at the graph of the sine function, we definitely see that sine is not a 1 to 1 function. No matter where I draw a horizontal line, it's going to intersect that sine graph in infinitely many points. So what we're going to do is we are going to restrict the domain of the sine function in order to make it 1 to 1. And that's something that we did way back in chapter 1. So the way we want to restrict the domain of the sine function is we want to take a look at the graph of the sine function in between negative pi over 2 and pi over 2. So when I take a look at the sine function on that interval, okay, which is what we have in red there, um, we've restricted the domain of that function in order to make sine 1 to 1. Sine is 1 to 1 on that interval from negative pi over 2 to pi over 2. So if we look at the domain and range of the portion of the sine graph in red, the domain of that function is the closed interval from negative pi over 2 to pi over 2. And the range of that function on the interval is going to be the closed interval from negative 1 to 1. Well, when we look at that portion of the sine graph, there are 3 points that lie on that part of the sine graph. We have the ordered pair negative pi over 2, negative 1. We have the ordered pair 0, 0, and that point over here is at pi over 2, 1. If we take those 3 points and we want to find the corresponding points on the graph of the inverse function, all we have to do is take those 3 points and interchange the x and y coordinates of those 3 points. So when we switch the x and y coordinates of those 3 points, we're going to get the ordered pair negative 1, negative pi over 2. For the second point, when we switch the x and y coordinates, we get the ordered pair 0, 0. And then for the third point, when we switch the x and y coordinates of that point, we get the ordered pair 1, pi over 2. Now, the relationship between the graph of a function and the graph of its inverse is we can take the original function and reflect that graph about the line y is equal to x. And that should give us the graph of the inverse function. So when we take the graph of that portion of the sine function in red and reflect it about the line y is equal to x, our resulting graph of the inverse is going to look something like this right here. Okay, so there are 2 ways that we can denote the inverse sine function. The first way is y is equal to sine. Again, it looks like an exponent of negative 1, but it's not. Again, that's how we denote an inverse. So that's sine inverse of x. Or the other way that you'll see books represent the inverse sine function is by writing it as arc sine. So y is equal to the inverse sine or y is equal to the arc sine are exactly the same thing. Okay, and if you look At the domain and range of the inverse sine function or the arc sine function, the domain, the x values on that graph are the closed interval from -1 to 1, which was the same as the range of the sine function. And then the range of the inverse sine function is going to be the closed interval from -π/2 to π/2, okay, which was the domain of the sine function. And another way for us to look at the relationship between inverse sine and sine, y is equal to the arc sine of x, or y is equal to the inverse sine of x if and only if the sine of y is equal to x. Okay, now just really quick, I want to make sure we're clear on the difference between the sine function and the inverse sine function. When we have the sine function, let's say we want to take the sine of π/4. Okay, we should be able to figure out the sine of π/4. The sine of π/4 is going to be rad2/2. That's something that we went over in previous lessons. So when we have a sine function, the input for the sine function is going to be an angle measure of some sort. Okay, so our input in that case is π/4, which is an angle measure. And our output is going to be a ratio. In this case, with sine, the ratio is like the side opposite over the hypotenuse. So again, with sine functions, our input is an angle measure of some sort, and our output is a ratio of some sort. That's going to be different for an inverse sine function. So with inverse sine functions, let's say we want to find the inverse sine of rad2/2. The inverse sine of rad2/2 is going to wind up being π/4. And we'll take a look at why that's the case in a little bit. But with inverse sine functions, our input is going to be a ratio of some kind, and our output is going to be an angle measure. Okay, so again, that's the difference between a trig function and an inverse trig function. With trig functions, our inputs are angle measures and our outputs are ratios. With inverse trig functions, our inputs are ratios and our outputs are going to be angle measures of some type. Okay, so let's do the same thing with cosine. We'll run through this a little bit faster because there's a little less to explain here. So the graph of y is equal to the cosine of x is in black. Again, it's not a one-to-one function, so we need to restrict the domain to make it one-to-one. So the way we restrict the domain of the cosine function is we're going to look at the graph of cosine in between 0 and pi. So if I take a look at that portion of the cosine graph only, which is that graph in red, the cosine function is one-to-one on the interval from 0 to pi. Okay, so thereby making its inverse a function. So we've restricted the domain here to be the closed interval from 0 to pi. The range, the y values on that graph are between -1 and 1. And then we want to take the 3 points on that graph. So we have 0, 1, π/2, 0, and then pi -1. We're going to switch the x and y coordinates of those 3 points to plot the 3 points on the graph of the inverse cosine function. So when we switch the ordered pair 0, 1, we get 1, 0. The ordered pair π/2, 0 gives us the point 0, π/2. And then when we take the point pi -1, when I switch the x and y coordinates, we get the ordered pair -1, pi. And then when we take that graph and reflect it about the line y is equal to x, our resulting graph of the inverse function is going to look like that right there. Okay, so when we look at the inverse cosine or the arc cosine function, the domain of that function, so the inputs are going to be the closed interval from -1 to 1. The range or the outputs or the y values covered up by that graph are going to be the closed interval from 0 to pi. And again, just like we said with the arc sine function, y is equal to the arc cosine of x if and only if the cosine of y is equal to x. Okay, onto the graph of tangent. So we have two periods of the graph of tangent here as well. Again, just like with the sine function and the cosine function, tangent is not one-to-one. Just generally speaking for the graph of that function. So we have to restrict the domain of that function in order to make it one-to-one. So if we take a look at the graph of tangent in between the vertical asymptotes at x is equal to negative pi over 2 and x is equal to pi over 2, if I restrict the domain in between those two x values, we see that tangent is one-to-one. It passes the horizontal line test. So we've restricted the domain here to be the open interval from negative pi over 2 to pi over 2. And then the range values, or the y values that get covered up by that graph on that interval, are all real numbers. So that's going to be the open interval from negative infinity to infinity. Well, when we take that graph, reflect it about the line y is equal to x to sketch the graph of inverse tangent, where the graph of tangent has vertical asymptotes, the graph of inverse tangent is going to have horizontal asymptotes. So the graph of inverse tangent is going to have horizontal asymptotes at y is equal to pi over 2 and y is equal to negative pi over 2. And then when we look at the graph of tangent, as the x values go to negative pi over 2, the y values go to negative infinity. So as the y values go to negative pi over 2, the x values are going to go to negative infinity. So that means our graph is going to look like that. The graph of tangent passes through the origin 0, 0. So when I switch the x and y coordinates, that means that the graph of inverse tangent also has to pass through the origin. And then as the graph of tangent, as the x values go to pi over 2, the y values go to infinity. So when we switch the x and y coordinates, as the y values go to pi over 2, the x values are going to go to infinity, which is going to make the graph look like that. And then when we take a look at the domain and range of the function in red, the domain, the x values are all real numbers. And then the range values, the y values, are going to be the open interval from negative pi over 2 to pi over 2. Okay, so you don't need to know like what the graph of inverse sine, inverse cosine, and inverse tangent look like per se. I just want to talk about kind of the math behind what the inverse sine, inverse cosine, and inverse tangent, like what the graphs look like, and then the relationship between each of the trig functions, sine, cosine, and tangent, and their respective inverse functions. Okay, but there are some graphs that I want you guys to remember when it comes to evaluating inverse sine, inverse cosine, and inverse tangent functions. And if you take a look at the graphs that we have, or the coordinate planes that we have in blue down below, I want you to remember these graphs because I think it makes it easier to evaluate inverse sine, inverse cosine, and inverse tangent functions. Okay, so for inverse sine, we said that the outputs for inverse sine have to be between negative pi over 2 and pi over 2. So I want you to remember this graph here. The outputs for inverse cosine, we said, had to be between 0 and pi. Okay, so I want you to remember this graph here. And then the outputs for inverse tangent have to be between negative pi over 2 and pi over 2. So this is negative pi over 2. That's pi over 2. And I want you to remember that graph for inverse tangent. And the reason that I want you to remember these is it's going to tell us like where the outputs are going to be for each of these inverse trig functions. Okay, so again, for inverse sine, it's from negative pi over 2 to pi over 2. For inverse cosine, it's between 0 and pi. For inverse tangent, it's between negative pi over 2 and pi over 2. Okay, so how do I use these graphs to help me evaluate inverse trig functions? If my ratio, so my input values for each of these functions, okay, we know that for the graph of sine, we know sine is positive in quadrant 1. We know it's negative in quadrant 4. Okay, for the cosine function, we know cosine is positive in quadrant 1 and it's negative in quadrant 2. And for the tangent function, we know tangent is positive in quadrant 1 and negative in quadrant 4. Okay, so what does that tell me? Well, that tells me whenever I am evaluating inverse trig functions, if the input for, and let's say an inverse sine function, if the input is positive, the output is going to be an angle in quadrant 1. If the input is negative, the output is going to be an angle in quadrant 4. Okay, for the inverse cosine function, if the input, so if the ratio, which we're inputting into that function, is positive, that tells me that the angle output is in quadrant 1. If it's negative, it tells me that the angle output is in quadrant 2. And then for the inverse tangent function, if the ratio that we're inputting into that function is positive, it tells me that the output is going to be an angle in quadrant 1. If the input is a ratio that's negative, the output is going to be an angle that is in quadrant 4. Okay, so if you keep track of like what those graphs look like, it's going to tell you what quadrant your output for inverse sine, inverse cosine, and inverse tangent, it's going to tell us what quadrant that angle is going to lie in. Okay, so we'll take a look at some examples of each of those in the next video.